In the modern food industry, consumers demand healthier, low fat alternatives that maintain the texture, creaminess, and mouthfeel of traditional high fat foods. But how do food scientists create low fat products that still taste delicious? One key challenge is emulsion stability, ensuring that tiny droplets of fat, water, and stabilizing agents remain evenly dispersed without separating over time. This is where microfluidics plays a revolutionary role in food formulation, allowing precise control over emulsion properties to create better, more stable, low-fat foods. Emulsions are mixtures of two immiscible liquids, like oil and water, stabilized by emulsifiers such as proteins, polysaccharides, or phospholipids. In products like mayonnaise, salad dressings, ice cream, and plant-based dairy alternatives, achieving the perfect emulsion is crucial for maintaining texture, shelf life, and sensory appeal. Traditional methods of emulsion production involve high-speed mixing, but these approaches often lack precise control over droplet size and uniformity, leading to instability. Microfluidics, on the other hand, enables precise, controlled formation of nano and micro-sized droplets, improving emulsion stability, consistency, and efficiency. How does microfluidic emulsion technology work? Microfluidic devices contain tiny channels that allow fluids to flow through and mix under highly controlled conditions. Using droplet-based microfluidics, researchers can fine-tune the droplet size, distribution, and interfacial properties, optimizing the stability of low-fat emulsions without relying on excess stabilizers or artificial additives. For instance, double emulsions, where water droplets are encapsulated within oil droplets inside a water phase, can be engineered to mimic the creamy texture of full GAT foods while significantly reducing fat content. A great example of microfluidics in action is in low-fat dairy alternatives. Traditional low-fat milk often lacks the richness of full-fat milk due to its reduced fat globule content. Microfluidic processing can be used to design fat droplets with optimized structures, improving the texture and creaminess of low-fat dairy or plant-based milk. Similarly, in ice cream production, microfluidics enables precise fat droplet stabilization, preventing the formation of large ice crystals and ensuring a smooth, creamy consistency even with lower fat levels. This technology also benefits vegan and plant-based foods, where achieving the right emulsion texture without dairy fats can be challenging. By using microfluidic techniques, food scientists can create stable emulsions from plant oils, proteins, and polysaccharides, mimicking the mouthfeel of dairy products while maintaining clean level and natural ingredient formulations. Beyond dairy, microfluidics is transforming low-fat salad dressings, sauces, and spreads. Many low-fat dressings suffer from phase separation, where the oil and water components separate over time. With microfluidic formulation, food scientists can fine-tune emulsifier concentrations, pH levels, and droplet interfaces, leading to more stable, longer lessening emulsions with better sensory properties. Why is this important? As consumers become more health conscious, the demand for low-fat, natural, and clean label foods is increasing. However, reducing fat content without compromising taste and texture has always been a major challenge in food science. Microfluidics provides a scientific and technological breakthrough, offering precision, efficiency, and sustainability in designing the next generation of healthier, better-tasting food products. Could microfluidics be the future of food innovation? As this technology continues to develop, we may see a world where low-fat foods taste just as rich and indulgent as their full-fat counterparts without the drawbacks of excessive calories or artificial additives. Emulsions are mixtures of two immiscible liquids, typically oil and water, stabilized by emulsifiers such as proteins or surfactants. Low-fat food products rely on stable emulsions to maintain texture, mouthfeel, and shelf life. However, reducing fat content often compromises stability, leading to phase separation. Microfluidic technology provides precise control over droplet formation, dispersion, and interfacial properties, allowing the creation of uniform and stable emulsions. By optimizing factors such as droplet size, emulsifier concentration, and shear forces, microfluidic systems help produce low-fat emulsions with improved stability and sensory properties. Microfluidic techniques have been used to produce stable, low-fat mayonnaise with a fine-tuned oil droplet distribution, mimicking the texture of full-fat versions. Emulsions in food are like well-mixed paints. If not properly stabilized, the components separate over time, leading to an undesirable texture. Not to mention, traditional emulsification methods such as high shear mixing and homogenization often produce broad droplet size distributions, leading to inconsistent textures and stability issues. Microfluidic emulsification offers precise control over droplet generation, ensuring uniformity in size and distribution. By adjusting flow rates, surfactant composition, and channel geometries, microfluidics enables the production of monodisperse emulsions with enhanced stability and controlled rheology, crucial for low-fat food formulations. Microfluidic emulsification has been applied in dairy products such as yogurt and cheese spreads, ensuring consistent texture while reducing fat content. This process is like using a fine sieve to create perfectly uniform grains of sugar instead of crushing large crystals by hand. In low-fat emulsions, stabilizers such as proteins, phospholipids, and polysaccharides play a key role in preventing coalescence and phase separation. Microfluidic platforms allow precise screening of surfactant combinations to identify optimal formulations for long-term stability. These systems also enable the study of protein adsorption dynamics at the oil-water interface, improving the design of novel food-grade stabilizers that enhance emulsification while maintaining nutritional benefits. Whey protein stabilized microfluidic emulsions have been developed for low-fat ice creams, preventing ice crystallization and maintaining smooth texture. Emulsifiers act like glue in a brick wall, keeping all components tightly bound to maintain the structure. Shear stress during emulsification directly affects droplet size and stability. Microfluidic devices allow precise control over shear forces, enabling the formation of nanometer to micrometer-sized droplets. Lower shear rates produce larger droplets, while higher shear rates generate smaller and more stable emulsions. This tunability helps optimize the mouthfeel and viscosity of low-fat food products without requiring artificial thickeners. Microfluidic control of shear stress has been applied in plant-based dairy alternatives to optimize the texture and creaminess of almond and oat milk. Shear stress in emulsions is like kneading dough. The right amount ensures a smooth texture, while too much or too little affects the final product. One of the main challenges in low-fat emulsions is preventing droplet coalescence and phase separation over time. Microfluidics enables the study of interfacial tension, electrostatic interactions, and steric hindrance to optimize stabilizer efficiency. This approach allows the formulation of emulsions that remain homogeneous even under varying storage conditions, preventing issues such as creaming or sedimentation. Microfluidic studies on lecithin-based emulsions have led to improved stability in low-fat salad dressings, preventing oil separation over extended storage periods. Preventing coalescence in emulsions is like keeping bubbles separate in a bubble bath. Without the right conditions, they merge and collapse. Low-fat emulsions often suffer from rapid flavor degradation and nutrient oxidation. Microfluidic encapsulation techniques enable the controlled embedding of bioactive compounds such as vitamins and essential fatty acids within emulsified droplets. By fine-tuning shell composition and droplet size, microfluidics enhances the retention of flavors and nutrients while protecting them from degradation due to light, oxygen, and temperature fluctuations. Microfluidic encapsulation has been used in low-fat chocolate formulations to stabilize cocoa butter alternatives and enhance flavor release. Encapsulation works like a protective shell around a pearl, preserving its luster while preventing damage. Traditional emulsification techniques require high energy input, increasing production costs and environmental impact. Microfluidic emulsification offers a low energy alternative, reducing mechanical stress while maintaining high emulsification efficiency. By minimizing energy use and ingredient waste, microfluidics aligns with sustainable food processing goals, making it ideal for the development of next-generation low-fat foods. Microfluidic emulsification has been implemented in the production of plant-based dairy alternatives, reducing processing costs while enhancing texture and stability. This method is like a high-efficiency light bulb, delivering the same performance while consuming far less energy. Texture and mouthfeel are key factors influencing consumer acceptance of low-fat foods. Microfluidics allows the precise modulation of droplet interactions, viscosity, and surface properties to mimic the richness of full-fat products. By fine-tuning the composition and structure of emulsions, researchers can create tailored sensory experiences that improve palatability without increasing fat content. Microfluidic optimized emulsions have been used to replicate the creamy texture of full-fat dairy products in reduced fat cheese formulations. This technique is like tuning the settings of a music equalizer, adjusting individual elements to achieve the perfect balance. Advancements in microfluidic emulsification continue to expand the possibilities for food science. Emerging trends include the use of smart emulsions with dynamic stability, plant-based emulsifiers derived from sustainable sources, and AI-driven microfluidic platforms for real-time formulation optimization. Future developments will focus on personalized nutrition, enabling customized emulsions tailored to individual dietary needs and preferences. AI-assisted microfluidic screening is being explored to design functional emulsions for sports nutrition, optimizing hydration and energy release. The future of microfluidic emulsions is like personalized meal plans, precisely tailored to meet individual nutritional and sensory needs.